really enjoy to see so many people here.
Okay.
So I want to thank Silicon Valley Machine Learning Meetup to host this event and Hack Dojo to provide such a great venue over here. So my name is Tsai. I'm going to talk about multinomial logistic regression in Spark. And I'm a machine learning engineer at Alpine Demo right now. So yeah, so I'm going to talk about that. And if you have any questions, just stop me, ask me any question anytime. So before we started, I want to take a few seconds to talk about my company because we are doing lots of interesting things, and I just want to share with people. So we are doing the cooperative and co-free advanced machine learning solution for big data. So basically, everything is web interface. So you can connect your Hadoop dataset to different algorithms, run computation metrics, all the stuff. So the technology we are using are Scala, Java, Arca, Spray, Hadoop, Spark, of course, Pig, Scoop, and our platform is running on different vendors of the Hadoop, like Cloudera, Hodenwork, Pivotal HD, mapR. So we actively, work with the open source community, and we try to commit or contribute back most of the algorithm we develop in our company. So we already commit LBFGS, which is the optimization package in Spark, and also we help to fix a couple of bugs in Spark and try to do something, some basic functionality inside analytics, like how to deal with transformation, how to deal with PMML, this type of stuff. And we are also working on different algorithms like multinomial logistic regression, which is not in Spark yet because it requires some infrastructure change. But we are going to contribute back. And we also work on GOM, decision tree random forest. So we are also a maintainer of several open source packages, including Chorus, SVT plugin for JUnit test. So basically it's for Jenkins. So whenever you do SVT test, run through everything, you can generate a report, which can be read by Jenkins. So it's also used by Spark, this package for SVT plugin. Yeah, so since we are hiring machine learning engineer, data scientist, UI UX engineer, front-end developer, infrastructure engineer. So if you are interested, please send me email. Okay, so let's start. Okay, so basically, machine learning with big data. Before Spark come out, people typically using Hadoop, mapReduce to do machine learning. Either they develop in-house or they use some external package like mapFu. But the problem is that in general, doing machine learning with Hadoop are really slow. It's not avoidable. It's not a flaw of mapFu or whatever because the I/O overhead in the Hadoop is really big. Whenever you are working on iterative algorithm, and that's algorithm is iterative, like k-means or most of the optimization, process are also iterative. So basically, you need to look through the data so many times in order to get a result. But each time in Hadoop, when you look through the data, you are basically reading the data again. From the disk I/O. So it's the problem. So lots of people come out with some trick to avoid this kind of problem. Either they can do some sample of the data and train a model with some sample of the data. That sometimes give you good result. But in this case, why do we do big data, right? And some people also do some approximation in order to train the result in a reasonable time. But sometimes doing this kind of approximation can give you worse result compared with just doing some sampling. So okay, so let's talk about Spark. So Spark is a good framework which can help user to cache the data on the second iteration in memory. So in the first iteration, you read everything from the HDFS, which is the disk. The I/O is really slow. But on the second iteration, whenever the memory is big enough to cache the data, it's gonna cache into the data. But you guys probably gonna ask, what if the cluster has smaller data than, smaller memory than the data set? So in this case, Spark gonna automatically deal with it. So it's gonna split the data into HDFS system. So the worst situation is like Hadoop, MapReduce. And we do some benchmarks. So in Spark, compared with Hadoop, it's almost 100 times faster. And we are being able to train the real model without doing any approximation. So it's real logistic regression. So I'm going to talk about the basic idea of what logistic regression looks like. So you can think about it. So on the right-hand side, so you have a bunch of data, which is either positive or negative. And then you can find out a point, hyperplane, which can, separate the data really nicely, like the one we saw over there. And you can define the distance between the data point to the hyperplane as the d equal to as1 plus bs2, this kind of, high school math. So after doing that, okay, the whole idea of logistic regression is that you can do the prediction by modeling that such that if your data is far away from the hyperplane on one side, then you have higher probability to classify as positive. If you have, if your data is on the hyperplane of the other side, you're gonna have lower probability to classify as negative. So one really easy way to do it is that you can use logistic function, which is defined by exponential d 1 plus exponential d. Okay, so in this case, okay, the probability that you're gonna classify as positive gonna be how far you are away from the hyperplane by the equation, and the formula, the logistic function, look like the left-hand side picture. So then, how do we train the model? This is the way we do prediction, right? So how do we train the model? So by using this equation, we know that each point gonna give you a probability, right? Either it classified as positive or negative. We can get a probability. So for the training data set, it's labeled. So all the data, the result is labeled data. So you can know the overall probability of the whole system by multiplying all the probability of each sample. So what we are actually doing is that we are moving around the hyperplane to maximize the overall probability. The probability is how good the model fit with the data by doing this. If you are training the support vector machine, the idea is that we are also moving the hyperplane, but what we are fitting is the margin of the data set. So basically the idea is kind of cheap. So how can we do it? So as we already talked about, you have a data set X and label Y, and then you can define the likelihood by L, which is just multiply all the probability of each sample. But it's really difficult to solve this problem. So in general, we take them because, okay, if you look at the equation, likelihood cover with all the sample, and it's multiplied by all of them. So how can you solve it in parallel? It's difficult. So what we can do is that we can take the log of the equation, and then it becomes summation. So you get a log likelihood. And instead of maximizing the likelihood, we can minimize the log likelihood. So it's really good because in this case, we can compute log likelihood for each sample disputed. And then in the end of the day, we just sum them up. So we can know the log likelihood of the whole system. So any questions so far? Okay, if no, I'm gonna continue. Okay, so it's become an optimization problem. So you get log likelihood. How do you want to minimize it? And it's a standard complex optimization problem. So there are a couple of ways you can address this problem. For example, you can do the simple gradient descent, LBFGS, which I implemented in Spark, or ocean-wide limited memory quotient method. Those LBFGS and OWLQN are so-called quotient method. So the conversion rate is super linear. It's not linear. Like gradient descent, the conversion rate is linear, so it's converging really slow. And you can also do a coordinate descent or trust region Newton method. And all of them are so-called first-order minimizer. So what first-order minimizer means is that you only require the loss function, and the loss function is the whole log likelihood, and also the gradient of the log likelihood. This is the only information you need in the optimization process. And for the second-order minimizer, like Newton method, you need to require the loss function, the gradient, and the Hessian of the loss function. So basically, gradient is the first derivative of the log likelihood, and Hessian is the second derivative of the log likelihood. So in this case, you can update it, the weight by the equation over here. But the problem is that for the second order method, it doesn't scale well. Vertically. So, however, it scales well horizontally. Horizontally means the number of the training data, because it's dealt by Spark or any parallel framework. So you can just distribute it and then compute the Hessian gradient or loss function of each data point, and just aggregate them at the end of the day, and you update the weight. But for vertically, the problem is that lots of training data set has bunch of features. So for example, we have a customer, they have each URL is a feature, and then whether the visitor visit the URL or not, it can be 1 or 0. How many times they visit it, it can be another number. So it's really sparse. But the number of the URL can be couple millions. So in this case, Newton method or the second order method doesn't scale well, because you need to calculate Hessian, and the dimension of Hessian is square of the number of the columns you have. So for example, if you have 1,000 columns, then if it's a binary classification, then the number of the dimension of H gonna be square of 1,000. It's gonna be really large. And also recently there are lots of applications, including document classification, some linguistic problem, this kind of problem. So basically you have so many columns. So basically in this case, the second order method doesn't work well. So the only way we can do is using first order method. And however, the gradient descent converging really slow. So that's why we do quasi-Newton method. Okay, so I'm gonna briefly talk about LBFGS. So it's a quasi-Newton method, and actually it's actually carry out the Hessian, not explicitly. So basically, the Hessian matrix is approximated by the previous step of the gradient evaluation. So that's why it's converging faster than gradient descent. Because if you do gradient descent, in each update, you only carry out a gradient and use those information. You don't use any previous gradient for the current update. But in LBFGS, you take the previous M gradient as the information to compute the next step. So that's why it's called quasi-Newton method. So it's approximate Hessian actually. And we like to do open source. So the LBFGS is merged in Spark right now. So you guys can try it out. It's already in the Spark 1.0. And they plan to remove the gradient descent and use LBFGS as the default optimization package for the next release. Okay, so let's go back to training binary logistic regression. Okay, so as we said that the log likelihood gonna sum all the log of the probability for each sample given the weight and S and Y. S and Y are the training data, which is known. And after doing some math, right, you can get a lovely equation over here. You can get this equation. And because we want to do optimization, right, so we need either, we need to compute a gradient of this log likelihood and Hessian of this log likelihood in order to do optimization. Okay? So you can do some math and you can get a gradient for each sample. So over here you can see it's summing over k from 1 to n, and each of them is one sample. And those samples are distributed in a cluster. So each node gonna have its own sample. So basically everything is, you can sum them, individually and then aggregate it at some point. So GI means that the gradient of the I column, and then you can do the math. Get this one, and you can get Hessian. So what you do in a cluster is actually compute YK, SKI, this type of stuff individually and sum them up in a reduced space. So any questions so far? No, okay, good. Okay, then let's talk about overfitting, the problem of the overfitting. Let's say you have a sample which is totally separatable by the hyperplane, like this one, okay? And then you get a model of the weight, which already, can predict everything really perfectly. And the equation is something like this, SW. And then the problem is that if the data is totally separatable, then you can always multiply by a constant into this equation, GD, and then you're gonna get this prediction. What it means intuitively is that you can change how sharp is it for the probability, disputing. Yeah.
Did you run into saturation of the regression function?
Pardon? This problem?
Do you run into a saturation situation with a large number of input vectors?
I don't get you.
Saturation.
Saturation?
Yeah, so you're taking the gradient of the logistic function.
Yeah.
And the function is almost flat at the extreme ends.
Oh, you say become like the real one, right? Really? No.
Yeah. So around there at the top, and at the bottom, the
yeah,
is almost zero.
Yeah, exactly. That's the problem. So it's sometimes called. So you can make it, So basically, in this case, the weight gonna become infinity. So lots of time when you train logistic regression, you're gonna get really high weight. The value is gonna be going to really large. So the problem is like this because of the overfitting. So you can always multiply by a constant if the data is totally separatable, and then you still get the same prediction. So each time when you do an iteration, you get higher and higher, let's say lower and lower log likelihood. So basically the model fits better and better, but it's already, giving you the best prediction. But in this case, just one more. So in this case, you are just overfit the data, so you cannot generalize the model. Right? So you want to make the boundary a little bit blurred. So basically, you want to have some over here the boundary. You don't want to make this boundary, this hyperplane part become 1, this hyperplane minus become negative. You want to make it a little bit blurred. So that's why you want to add regularization. Yeah. So
yes, how does this approach compare to the traditional L1 and L2 regularization?
Yeah, so I'm going to talk about that. So this is the way you can solve this problem. So in general, people solve this kind of overfitting by regularization. So you can either do L2 or L1. So basically, you add another penalty term in the last function, right? So you want to minimize the last function, but the regularization also penalizes finding a really big weight. So if the weight becomes larger, you penalize the log likelihood. So which means you can tune in that, how, tune in the regularization. So yeah, so L2 and L1, the differences is that in general, L1 can give you really sparse result. So it's called so so in general, for L1, people use it for something like if you have millions of columns, you do L1, and then you get really sparse result. So you can use it for feature selection, for example, and also you can find out which are the important for your prediction. Yeah, but the problem is that for L1, it's not a trivial problem because L1, the last the regularization loss function is not differentiable. So there's no well-defined gradient on the 0 point. So that's why people come up with all kinds of different methods. So for example, let me go back. So for example, like Wilson-Wise limited memory continuity method is a variant of LBFGS, but it can deal with the L1 regularization. So when you do the optimization, OWLQN can predict which order you should step instead of closing the boundary. Because when you do the optimization and close the boundary, the behavior is not well defined. Or you can do gradient descent with soft threshold, bunch of different ways to solve it. It's a really popular academic problem. Or you can do trust regime in the method. Those are designed to solve L1 problems. And we are working on OWLQN right now, so we're gonna also open source it in the Spark community. Okay, so I'm gonna talk about something more fun. So some Spark API and Scala stuff. So it's probably gonna be, not that dense compared with the math. Okay, so there are two important API, which is map and reduce. For how many of you guys are writing Scala over here? Well, it's quite a lot. Okay, so probably you guys are already familiar with map and reduce over here. So basically, it takes a function in map. It's basically take a function, and then it's gonna generate another result. So basically, you can do. Let's say you have an array. You can do array.map, and then you take a function, and function take an input and generate an output. So you can do any transformation inside map. And reduce is that you take two elements and combine them into another element. So it's a rule. So basically, reduce has to be, commutative and associative in order to get a right result over here. So, okay, let me show you how to do the count of the mean of bunch of number in Spark. So the first line, the API is really simple and really scalable. So the first line is that you take an input and you read it in Spark. So you do text file, sc.text file, open and file inside HDFS. Okay? So once you have the file, then you get the input. So the second line is that you want to cache it. So you can do input.cache. So at this time, the data is not actually cached. So basically, the data only cache when you do an action. It's lazy evaluation. It's lazy evaluation. So so the data will be cached after the reduce. I just show it over here. So it doesn't matter over here because we don't recycle the data. Twice. But in general, if you do some algorithm and if you want to recycle the data, you want to cache it in the memory, you just do that cache. It's pretty simple. Okay?
So going back that, what to work with in Spark.
Yeah.
Using this
Spark content.
Scala that you're showing is an X data array. So you have to actually pre-process and keep it in order to cache it.
Oh no. So.
In other words, if I had like raw data, which is I'm merging with Python.
Oh, okay. I got
I
it.
deal with that.
Okay. So what over here, the input gonna be okay. Let me tell you how it works. So over here is a good question. So the input gonna be an RDD of a string. So yeah, so RDD. What RDD means is it's kind of like array. You can think about RDD as an array, but this array is distributed in the cluster. So each worker has its own data, and it's read from HDFS. So you can think about it in HDFS, right? You have a block. So each worker gonna load its own block into the memory, and then store over there. So it's kind of like an array, but it's distributed. So you don't need to deal with the actual implementation. But you can think about input is an array of string, and each element is one line on the text file. Because over here I do text file, text file. So you are opening a text file. So basically input is an array, but it's distributed. So it's not actually in your local machine, it's in a distributed environment.
I will need to code the Python to actually create that array and distribute it, right? Before I start.
I'm not sure how Python API works. Yeah, I never use Python, sorry for that. Yeah, but for Scala, that's how it works. So input is RDD of string, and it's just array of string, distributed array of string. Okay? And the second one is that trying to cache it whenever you touch the data. So when you run input equal to SC.text file, you don't actually cache the data, or you don't do anything. It's just waiting over there until you touch the data. So, but I'm just telling that whenever you touch the data, you want to cache it inside a cache RDD. So the type of cache RDD gonna be the same as input. Okay? So over here, what I did is that, so the raw data is function of the number in each line. Let's say this way. Okay, so what I did is that cache RDD.map. So you can pass a function. So over here is anonymous function. So you pass a function which takes each line and you generate a tuple. So you generate line.toDouble and 1. Okay? And then you reduce it later. So the reduced code can be run locally inside the executor or globally when you aggregate the result from each partition or each mapper, actually. Okay? So over here, what I did is that you take A and B, and the type is the output of this function. Okay? So it's gonna be A and B gonna be a tuple as well. Okay? And now what you want to do is that A gonna be the value, you sum them up with the second one. And this one is the count. Because over here I generate the line and also the count. So assuming that the first time you generate the stuff, the count is equal to 1, right? So you can over here you do you are summing up the count. So you can visualize it in this way. So you have data 3, 2, 1, 5, and then you partition them as 2 partitions. So they are running in 2 different executor or worker. And then the first map, what the first map does is that you generate a tuple 3, 1, 2, 1, or 1, 1, 5, 1. And the reduced space gonna run locally first in a partition and then aggregate it. So you're gonna get 5, 2, and the other one gonna get 6, 2. Okay, and then you're gonna do another reduce again on the driver, which is the master, your master program controlling the whole thing. So you're gonna reduce everything and get 11, 4. But over here the problem is that okay, the reduce function currently in Spark. You are pulling all the data from from the map to one driver and sum them up over there. So the problem is that, think about it, if you have thousands of nodes, okay, and the driver, which is a single node JVM on your system, then I read each of the output of the mapper and then sum them up sequentially. So over here, the shuffle phase, or after shuffle phase, the reduce phase, the time big O gonna be ON, and N gonna be the number of the worker or number of the executor you are using. So it's not actually efficient, and right now it's not. But it's how Hadoop works right now. So Hadoop, each time you generate a key value pair, and then one of the reducer gonna be in charge of one key and sum them up, sum all the value up at some point. So it's not efficient. So imagine that we can do something like a tree aggregate. So these two can aggregate first, and then you get one result. So it's not running in the driver. And these two can join the aggregate result of these two, and then eventually you pour it into the driver. So it's called a tree aggregate. So it's going to be implemented in Spark issue 2174. So it's gonna be ready, I think, in Spark 1.1. And by doing the tree reduce, the time big O gonna be low, so it's more efficient and more scalable in terms of aggregate everything from the mapper. So yeah.
You always do tuples at a time?
Oh, I just do an example. You can do whatever you want. So you can, in general, what I did is that I can create an object to, something like a case class, for example, in Scala, or whatever object, to keep track of the data. And then in this case, A and B is the special object you have. And you want to generate another type, another object which has the same type of A and B. So you just write different combined rule in this case. So it's not necessarily a tuple. And I'm going to give you another example. So, yeah. So there are another API called mapPartition, which is more similar to Hadoop, map function. And it's sometimes more efficient. So for example, like over here, each line I generate in a tuple, which contains the value and the count. So the problem is that lots of times you're gonna deal with a really big data set, even in each line or in each sample. So in this case, you create some new object, destroy it, because when you apply reduce, you destroy one of the objects. So you're gonna run into some problem about garbage collection in JVM. It's really terrible. So it's really difficult to debug, but suddenly your program just doesn't run.
Yeah. Our question is, when are executors created, at which line they use the system actually create executor?
The executor. When you do reduce.
Okay.
So reduce is also in Spark. There are two sets of API. One is transformation. The other is called action. It's a good question. So all the transformation operation will never execute by themselves. So for example, what you can do, it's really good property. So you can do .map, .filter, bunch of different operations, but it's never going to be executed once before you run action. So the question is that all the transformation operator can be combined together, right? So you can do map. So basically you just can create an array of functions, and you apply each function, to the value you have. So in this case, you only look through the data once. So you don't need to go through the data a couple of times or cache it somewhere, because all the transformation can be combined into single action. So it's a good question.
So follow up. So as soon as reduce complete, all the executors are terminated.
Yeah, exactly.
Okay.
Yeah. Well, the JVM is not actually terminal. So the JVM will terminate until you do SC.close or something like that, because the executor gonna cache the data locally. Because you bring the data from HDFS to the memory and cache it in the executor. So yeah, good question. So any further question? Okay, then I'm gonna continue. Okay, so there's another API called mapPartition, which is really handy actually. So mapPartition is kind of like, map function. So basically, it's gonna give you an iterator to allow you iterate through the disputed data set in RDD or in a disputed array. So the question for doing that is that you can have a local variable or you can think about it, it's global variable in the partition to aggregate the result. So I think going to the example is easier, okay? So this is an example how to do the mean calculation using mapPartition. So over here, the code is that I do similar. I do input is equal to sc test file. I get it, and then I cache it. So and then I do mapPartition. So it's tag an iterator, which you can iterate through the whole data set. Okay. So what I did is that I have a local count and also local sum. But it's actually global to the partition over there. So each partition gonna have its own count and sum. Okay? And over here I do a for loop. Okay, I do a for loop. And then look through all the data in a disputed array. And each of them I just add it to the sum and add a count. Add another count. So the good thing over here is that you don't have overhead of of something like generating the tuple and then you apply reduce locally because you need to apply reduce locally first and then globally. And by doing this process, the problem is that you create a bunch of objects and destroy them. So it's not efficient and it's more, but the code is longer actually. Yeah, so it's more efficient. So you can do mapPartition. But there's another API called aggregate, which is much more beautiful. I mean, in terms of the Scala developer. So, so what aggregate does is that the type of aggregate is that you can initialize the 0 value, and then you have two operators. And the first operator is for combining the result locally in the partition. And the second operator is for combining the result globally between different partitions. Okay? So you can think about, look at the example. So I create a case class in Scala called aggregator. It's kind of like standard Java class, but it just helps you to do all the constructor, all the stuff for you. And you can initialize it by just aggregator and give you the value instead of doing something like new aggregator, all the stuff. So it's just a little bit handy. Okay, so in each aggregator you have a sum and count. So initial value is the aggregator with sum 0 and count 0. Okay, and the first operator is also a function, right? So it's tag aggregator, which is the input of the u and the object, and then another is the value. The value gonna be each line of the data inside the RDD. So over here is string because the RDD of string over here. Okay. So you get this tuple, which is input, and then what you do is that you want to return another aggregator, which has type you can see over here. So in this case, you can look through the data by doing that. So aggregate the sum gonna be equal to plus equal to the value to double, and then you aggregate the count as well. So over here, the aggregator gonna be always the same object. It's gonna recycle forever. So from the first one, you create an aggregate object, and then it's gonna pass it to the second line, third line, fourth line, fifth line. So essentially that's the idea. And then the combine operator is combine the result between two partitions. So it's tag to U object and then return single object. So basically over here you are combining two aggregators. So basically you just sum plus equal to sum and then call something like that. So it's a little bit handy. Okay. So over here, so I'm gonna talk about
Yes. How and why can you compare to traditional map forward or map reuse using just one?
You mean aggregator? So the internal implementation is mapPartition. So the internal implementation is mapPartition. So the performance is gonna be the same with mapPartition. But sometimes it's just more handy to use aggregator because Okay, so I'm gonna talk about the approach to parallelize the logistic regression or linear regression or SVML in Spark. So all of them are actually doing the same thing. So basically, okay, what you are doing is that you load the data, cache it in the memory in the first run, right? And then in each worker or in each executor, what you do is that you compute the gradient of each single row of the data or each single row of the sample. You get a gradient and also the loss function. Okay, so that's all. I mean, it's not difficult. So for each row of data, you compute the loss and gradient, and then you sum up all of them in a reduce. So in this case, the driver or the control node can know what is the summation of the loss function and the gradient, and then you pass it to the optimization process. So the optimization is running in the single JVM. So we only use parallel computation in terms of summing the loss function and a gradient of each sample. Okay, so basically most of the computation is doing the summation. So the optimization just takes 0 seconds. I mean, once you give the optimizer the gradient and loss function. So this is the whole idea. I mean, it's pretty simple. So I can show you the code. So it's before Spark 1.0. We use map and reduce. So it's pretty simple. You can see that. Okay, you take Y and features. Okay, as input. So each line of the array is RDD as well. But each line of the array is Y and feature, is a tuple. So Y is the predicting, result. I mean, either 1 or 0 over here. And features can be, bunch of color. It's an array. So it's bunch of color. So what you do is that, okay, you can compute the gradient and loss by defining the gradient function. And the gradient function is gradient.compute, passing the features over here and Y and the current weight. Right? Remember that when we write down the probability, all the log likelihood, all the dependency is only weight, Y and X. So you only need those 3 parameters to get the gradient and loss function. And then what we did is that we just reduce it by by each gradient and loss. So we just add it up. I mean, that's it. I mean, there's no magic over here. So this before Spark 1.0. And the problem by doing that is that every time we create a new object, new gradient, new loss, which gonna take some memory. And if we are training with this Spark data set, it's probably gonna run into some garbage collection issue. Okay, and you can also do it using mapPartition. So you can go through the code. I mean, there's no magic over here. So I probably can quickly go through it. Yeah, so it's doing the same thing. And then you can do it's in Spark 1.0. So we use aggregate in Spark 1.0. So the code is always concise, like mapPartition if you do it right. So basically, the whole idea is the same as what I talked about. Okay, then let's talk about multinomial logistic regression. So in binary situation, in binary logistic regression, we can derive this equation because we know the probability given weight and x. If the probability of predicting as 1 is equal to, we know this equation, and we also know this equation. So you just divide them up, and then you can get a linear function, which is x multiplied by weight, which is really beautiful. Okay, so it's comparing the probability of y equal to 1 and 0. Log of it is going to be a linear function. Okay, so how do we generalize it? Okay, so we can do the same thing. We can generalize it by comparing all the caches. So let's say right now we have k classes. Okay, either cat or student or teacher. You have 3 classes, for example, over here. But let's say we have a k class over here. And then each of them can compare with the class 0. You can randomly pick up any one of them as class 0. It doesn't matter because it's just doing the linear algebra. So you can do a transformation and get the same result actually. Okay, but for simplify everything, let's say we pick class 0 as the best class. And comparing all of our classes from y equal to 1 to k minus 1. So you can get k minus 1 equation over here, which is x multiplied by w1, x multiplied by w2, all the stuff. Okay, you can model multinomial logistic regression by this way. And doing some math, okay, you can get the probability of each class given this model, weight and y and x. So you get a probability over here. So in the prediction time, how do you do? Because in the prediction time, you already know the weight, you already know the x. Okay, so you're gonna run through all the caches and then see which one give you the highest probability, and then that one is the class you are looking for. Okay, so you are just looking through the y equal to 0 to k minus 1, and you get which one is the best class you are looking for. Okay, and this is for prediction time. But for the training time, how do we do it? So for training time, we do exactly the same thing as the binary logistic regression. So we also define the log likelihood and then plug in all the probability into the equation, and then eventually we'll get log likelihood assumption like this. Then you can get a gradient because right now you have 2 indexes, so gradient become a tensor kind of. So you have GIJ assumption like this is more complicated, and then you can get a Hessian of the loss function. So the basic idea is this. So any questions so far? It's kind of dense over here. Yeah, but this equation took me 1 or 2 days to get it right. So it's probably really worth it. If you want to implement multinomial logistic regression, you can take a photo and just type in all the equation, and you get the result. Because in there's a famous book by Hasty, the statistical learning. So over there, they just give all the equation up to here and say that it's pretty trivial to derive the equation by yourself. And I spent 2 days to get the right result and simulate it in the MATLAB. So it's not trivial. For him, probably it's trivial. Yeah. Okay, so yeah, so here is the benchmark. So I do a couple benchmark. So the first data is A9A data. A9A data is the standard academic data for doing benchmark of the logistic regression. So our cluster has 5 nodes, and each of them is 32 gigabyte memory with 4 core CPU, I guess. Okay, and the first data has 11 million rows and 123 features. So the non-zero element is 11% of the whole total data set. So which means 89% of the data is 0, or 89% of the power is 0. Okay, so I do some benchmark. So over here, so this one is the LBFGS with the dense representation of the vector. So it's one of the new features in Spark. which allow you to have a vector which is in the sparse format. So I just do benchmark between sparse and dense. So this line is the black one is LBFGS in dense format. So I can understand. So this actually is the log likelihood per sample, the average log likelihood. So you want to minimize it as possible as you can. And over here in the acceleration, it's time. So how much time you take to do the optimization. Okay? And this one, the blue one is LBFGS with sparse format. So you can see that, okay, for this, log likelihood, for example, like 0.35, the dense format takes 6 seconds. And then the sparse format takes 12 seconds. It's longer. The reason is the following, because in a sparse format, you only keep the index and the corresponding value. So when you do matrix multiplication, all this kind of stuff, you have overlay. So when the input data set is not sparse enough, it's showing that doing the dense format is better.
So I think the chart would be easier to interpret if you rotated the axis, right? Second would be more like y-axis.
Yeah, but in general, people have second acceleration and the time.
What do you say?
So over here is time, right? So over here you can see, okay, at some point the optimization doesn't do any work. It just going to the optimal point. So whenever you keep training, you just stay as we said, log likelihood.
Just to answer the question, one thing that is making here is speed of convergence rather than time taken for a particular configuration. So that's why I said on the x-axis. We're showing that this particular algorithm has much faster convergence to stable minimum.
Okay, yeah, good answer. Yeah. Okay. And the other one is gradient descent. You can see, it's converging slower than LBFGS.
So an actual question, we seem to have reached a stable minimum. Did we do any proof that that is indeed the minimum and that this algorithm is therefore optimal?
Oh, okay, good question. So logistic function is complex function. So you always can converge it to the global minimum.
If you're using something like an SVM for computation, then you're guaranteed a maximum separator at the global minimum. If we're not using an SVM,
what do you mean? So the last function over here is logistic function, and it's complex function. So you always can reach the global minima. But the problem, as I talked about, is that, okay, you can have a global minima of infinity, which is the overfitting problem I talked about. So the weight's gonna go to infinity. So you can see, okay, as time goes by, the log likelihood gonna always go smaller and smaller. So something like this. So you can always find out the next weight, which has smaller, log likelihood. But because it's complex, so you always find the global one. Okay? And here, I'm just talking about the number of iteration, what is the convergence of the LBFGS and gradient descent. So the other side is log likelihood, obviously, and in the X is iteration. So you can see LBFGS converging faster. Okay, it's the next data set, RCV1, which has 6.8 million rows, and how many features? I don't even, 7,000, something like 67, I don't know how to read it in English. Yeah.
68,000.
Or 68,000. Okay, yeah, lots of features anyway. So it's 0.1590 element. So in this case, the dense vector doesn't work anymore, because if you densify the data, it just runs out of the memory, because you can think about it, 0.15% on 0, and then if you convert it to dense array, how big is it? You need to multiply by 1,000 times, 10,000 times, I guess. Okay, anyway. So over here, LBFGS converge really fast. we get an accurate result in 10 seconds. And gradient descent just converging really slow, just not working. Yeah.
The log likelihood reducing doesn't tell much as as to the generalizability of the model, in the sense that the log likelihood can keep decreasing, and yet the test generalizability, the test error rate, or
Yeah. So this is something else we can do. I actually do it in-house, but for talking about optimization, people look at the log likelihood. But in terms of data mining, then you need to look at the accuracy, she compare the accuracy confusion matrix, for example, log curve with the test data, this type of stuff.
So is it comparable in this case? Was the accuracy the same as the?
So over here, the accuracy is getting higher and higher over here.
No, but this is still on the test data, right?
It's not in the test data.
It's
on the training data. So we do it in test data, but I forgot the number. Yeah, okay. But at some point it's just overfitting. Okay. So you need to add regularization actually. But it's just showing how the optimization process is working. So, okay, this is another data set, News 20. This one has really so many features actually. 1 million, I guess. Anyway, so 0.034 non-zero. So you can see, it's converging slower in LBFGS as well, but it's converging in 50 seconds. But for gradient descent, it just doesn't work. So originally I want to prepare a demo, but I don't know why the internet doesn't work well over here. So I actually prepared a photo. So here is one of the data set iris. I just duplicate it and make it really big. And then I have two operators. One is logistic regression. The other is using LBFGS. And then you can, our system gonna plot out the computer matrix for you. And you can see the accuracy, all the stuff. And we also have, as you said, right, we also have a random sampling operator. So you can random sample the data into 20% in the testing set, 80% is the training set with training, and then we can have the computation matrix connected from the model generated from the training set, and then using the data from testing set. So we can do it in our group. It's pretty easy, just 5 seconds or 10 seconds. Yeah. And over here, I just want to show is a Spark UI. So you can see the whole data is cached. So 100% is cached. And in the memory is 6.6 gigabytes. Okay. And over here, you can see, okay, it's for each iteration. So okay, so this is the first iteration. Multinomial logistic regression. The first iteration takes 20 seconds. So the reason is that in the first iteration, we are actually materialize the RDD. So remember I talked about that, okay? The cache will not cache until you do an action, okay? So in the first iteration over here, 22nd one, so we are loading the data from HDFS and cache it in the memory. So that's why it takes 20 seconds. And in the second iteration, it only takes 3 seconds because the data is cached. So when you do the computation, everything is done in memory. So you are looping through the data in memory, which is way faster. Okay, so yeah, conclusion. Yeah.
I'm sorry, in most data sets, is the cache, if you have a very big data set, then if you have a spillover, did you experience a significant slowdown when the spillover happened, or did you not experience any spillover?
Oh, okay. So yeah, data break guy or MLG guy, they do a benchmark from it. So essentially, even the data cannot 100% cache in the memory, it's still way faster than Hadoop. They have some benchmark.
No, but in your experience, did you experience any slowdown?
Yeah, it's gonna be slowed down, but still faster than Hadoop. But we don't actually do how many percent is cache. We probably want to do a benchmark at some point. So you can do 10% cache and then see the runtime performance. 20% cache, see the runtime performance, and then we can see how it break down. Yeah, it's a good question. Yeah, but we didn't do it. Okay, so conclusion. So we are hiring That is one of the goal I come here. Okay, and the second one is that Spark runs way faster than Hadoop, and Spark enable people to do iterative machine learning algorithm on big data set. And lots of problem actually become single machine problem. So for example, like optimization is single machine problem, but the bottleneck is always summing of the gradients or this type of stuff. And MLG provides lots of state-of-the-art machine learning algorithm, something like a k-mean. So they also have a k-mean plus k-mean parallel, not just k-mean. And they have linear regression, not just speed regression, AOS, cooperative filtering, knife-based. They have a bunch of algorithms. And lots of them are pretty good quality, it's commercial ready.
So which ML algorithm do you think is missing that should be there?
It's missing.
Is missing.
Lots of them. So right now they don't have this. They have decision tree yet. They just implement decision tree. But my coworker do some benchmark. It's work well compared with our in-house one. I don't know. Yeah. And also let me think about that. And they also don't have something like association rule, which is important.
How about ensemble, like random forest?
They don't have random forest, but we are planning to clean it up and contribute back to Spark. Yeah, they don't have random forest yet. So yeah, so
Very basic question if we go to the previous slide.
okay.
Why is the duration 19.2 seconds in the third stage?
Pardon? What do you mean?
I think it's the reading the argument. It's asking why is 19 is so high. It's
This
reading
one?
the
That's
argument.
the first. That's
Oh,
the,
this one?
That's the cache.
That's the reading the argument.
Yeah, this is the reading RDT. So as I explained, the first iteration is reading the data into RDT from the disk. So that's why it's so slow. Right? So the I/O is reading the actual disk instead of reading the data from the memory. Yeah.
So when you're writing new algorithms, how low do you need to go into the framework? I'm curious as to how necessary is working actually with JBLAS, or I noticed that Breeze also. So linear algebra libraries. How close to those? What kind of interaction with those do you need?
Okay, so basically the Spark or MLG, the internal linear algebra implementation is Breeze actually.
It's Breeze.
Yeah, it's Breeze. So
is that new? Was 1.0?
It's in 1.0. It's a new feature.
Yeah.
Yeah. So the idea is that we want to leverage on Breeze. Breeze is so fast, and you can call the native code. Install Intel, Breeze, library, or third-party one. So Breeze can call the native code. So that's why we want to leverage on Breeze to do the local, linear algebra. So for example, like I talked about, the sparse format, the sparse vector format over here are actually Breeze and sparse format. But we have a wrapper or MLG class to wrap around the Breeze. So essentially, user cannot directly use Breeze API. We only provide certain API user can use right now because we don't want to mess up the whole API. So lots of the stuff is there.
So then, in terms of that layering, are all of the wrappers that you would want currently there?
Yeah. Okay. Okay, and Spark provides a really good API in Java, Scala, Python, interactive Scala, Python Shell. It's pretty easy to do prototyping. For example, lots of time I use Scala, interactive Scala Shell to do some quick prototyping to see how things work. And Spark is an Apache project right now, so the momentum is really high. It has more committer compared with the Hadoop right now. So it says the activity is higher than all the open source big data framework. Yeah, that's it. Thank you.
I have a question.
Sure.
How do you deal with
fault tolerance?
Oh, fault tolerance. So it's managed by Spark. So basically, you load the data in RDD, right? And you can do lots of math or whatever. And then you can either do checkpoint. So you can checkpoint over there. You can do checkpoint. If you don't do checkpoint, you cannot do materialization from the beginning. But you don't do the recomputation for the whole thing. You just recompute the missing part of the data. So for example, you load.
But then, for example, imagine you have these 4 compute nodes.
Yeah.
And then you have a spare compute node.
Yeah.
And you start computing with 4 compute nodes, and then you say that you have to do 1,000 iterations.
Yeah. Okay.
Say that at the 500 iterations, one of the nodes dies.
Yeah.
Then you bring the spare node in there.
Yeah.
And then you start. That compute node has to start over and do those 500 iterations to catch up.
Yeah, you need to do it over, so you can do checkpoint to preserve it.
If you didn't do the checkpoint, it will have to do those 500 iterations to catch up with their own portion.
Yeah,
so
exactly.
the others are just waiting
until that is finished. Yeah.
And then after it reaches that spare one, the 500, then everybody keeps going.
Yeah.
So that's hopeless, right?
Yeah. So you need to checkpoint. Otherwise, this is all you can do. Yeah. So that's why it's better. Like the RDD is immutable, because once the RDD is immutable, then you don't guarantee that how you can go back from the beginning or doing the recover from the beginning. But there's some trick you can make the RDD immutable, because the performance wise it can be better.
So is there an API for this?
Yeah, there's API. So any more questions? Okay, cool. Thank you.